Recording in progress.
Good morning and welcome Physical Science 110. Today is October 18th. Today we are starting week 10. It is an important week because it's preparing for next week, which is the exam 2 that is. So last week we completed chapter 9. So far, after exam one covered the topics from chapter 1 to chapter 4. Exam 2 will cover chapters 5, 6, 7, 8, and 9. That's 5 chapters for exam 2. So from chapters 5 all the way to chapter 9. Chapter 10, which we're starting this week, is not part of exam 2, it's exam 3 actually, part chapter 9 that is. So that is the distinction. I think exam 3, which is way after this one's, which is going to be probably before the spring break, before the Thanksgiving break, I'm sorry about that, is going to be covering chapters 10, 11, 12, and 13. So you will have 4 chapters, and the last exam will be covering the last basically part of the class. I mean, exam 4 will be covering the rest of the chapters. So this is basically where we stand right now. So we have an important task this week, and that is to prepare for the exam. Which brings me to the first point of the discussion today is do the review, because there is a review that is actually available right now. And as usual, and as you have learned from the previous review, from the first review for exam 1, you will be receiving a mark for this review. And it's only one of 2 grades, either the full credit, which is 142 points, or nothing at all, or 0 points. So those are the 2 options. You do the review, regardless of how Canvas will give you for it, you're going to receive for the full credit. You don't do the review, then in this case, neither Canvas nor I can give you any credit for it. So you're going to receive a mark of 0 for the review. The review has 2 essential points. The first one is that it prepares you for the exam. And this is critical because the exams have a lot of weight on your overall grade. So you really would want to do well in the exams, and for that, do the review. So you see how it's connected. So it's very important that you guys do the review, just for this reason and this reason alone. The other thing also is the reviews, although they are part of the participation, which has a lot less weight than the exams, is actually graded a task too, graded assignment on its own right. And this is one of the easiest grades that you can get in this class. And that is to actually start the review. You can carelessly basically just start the review and close it and get a mark of 1 or 2 points, for example, in it, and you still get full credit for it. However, this is not recommended. You are urged to actually spend as much time as possible to do the review for the first reason, for the fact that it prepares you for the exam. So this is why it's important that you have. So again, the review is available right now on Canvas, and it's going to expire on Sunday night. So you have plenty of time to do your review. And take as much time as you need. However, start it early. Do not leave it to the last day and think about, oh man, I want to do the review now, because you will find it's a lot of things to do. So do not leave it until Sunday. I know some of you are working and taking other classes, but this is a class you're taking too. So you have to own it too. You have to allocate time for it too, during the week still. Because if we are in a normal class, you will be doing this reviews in class. So you'll be required to attend class and you'll be required to do this stuff in class. So in other words, you are enrolled in this class, you spend somehow money for it, so you really have to take care of it and take care of it as soon as possible. So again, the review is available on Canvas. You have to do the review for 2 reasons, as I mentioned. It prepares you for the exam, And the second thing is it helps you in a sense also because it's a graded assignment. Are we clear on this first task that we have to do? So this is part of your discussion item. Do the review for exam 2. Thank you, Alexis. Okay, so hopefully everybody is on board. As I mentioned before, I know a couple of you came a little late. And for those watching it recorded, the exam, which is exam 2, will cover chapters 5 through 9. Chapter 10 is not included in the review. However, there is that chapter, which is 10, is going to be included in the next time around. Okay, so chapter 10 deals with waves. So we're going to get into waves, we're going to get into optics, we're going to get into other stuff in there later on, but those things are not included in this exam. Okay, those are included in the next exam. So let me share the screen with you guys. Okay, I have had issues earlier with the internet, so if in case the internet freezes on you, or if the Zoom freezes, please do not leave because I will come back somehow. Okay, and it's going to be recorded. So if in case I am frozen, understand that whatever you say may be basically going to stay recorded. So in other words, do not share private information in there, okay? Related to your grades or something like that. So I'm gonna share screen. So this is where we stand. As you can clearly see, next week, the first topic, exam 2. Exam 2 is actually going to be available Monday and Tuesday. I know it was available earlier in the first exam a bit longer, but this time around is actually a little bit shorter. And we're going to go down and down. So because we're going to master this one, and we're going to have only less and less time for these things to do. Okay. Some of you might be working, some of you might be taking other classes. And I already mentioned this fact in here, the fact that this is a class also that you're taking. So you have to be responsible for it and you have to dedicate time for it. So this is something part of your responsibility. So do not leave it toward the end and then the last minute or say, okay, I'm working on Monday, I cannot do it on Monday. If the exam is going to be offered on Monday, you have ample of time to make arrangements, to plan for it. You work in the mornings, you have the evenings. If you have the working in the evenings, you have the morning. So you still have time to do these exams and all your tasks actually. So if you have problems with that, please work around them and find solutions in terms of scheduling. Okay. So let me open the objectives for this week. So we are all on the same page. As again, you can clearly see some of these things that they are a pattern now. Okay. The review has to do with magnetism from the previous week. We talked about magnetism, the sources of magnetism. It was something that is actually an interesting fact that Oersted, who was a high school science teacher, physics teacher, was basically following the textbook in there that electricity is one phenomenon, magnetism is another phenomenon. They are not related to one another. And he showed them with an experiment that here is a current, here is a magnet, they're not related to one another. One of his high school students, as after he left and the class was over, he went and moved the wire a little, and then he noticed that, actually noted that, hey, it seems like currents and magnetism are related after all. So our structure was wrong. All he did was just basically move the wires a little bit. Oersted now became famous after that to the point that some of the units in magnetism are actually named after him. So again, this is the thing is from the previous chapter that magnetic field or magnetism in general is rooted actually in currents. Okay, so again, this is the stuff that whatever we discuss in here, the PowerPoints, everything else, even in the review, they do not replace the fact that you have to read the materials from the book. That's why we require the book actually. Because sometimes I emphasize on a few things, but then when it comes to the exam review, you will see things that we did not talk about them that much, but they're included in the review. So do not come and tell me, hey, this thing, we didn't talk about it. I went through the recording from step to step and I didn't see you mentioning it once. I looked at the PowerPoint and I also didn't see you mentioning it once. Why? Because probably it's a minor point, but it's still there, part of the content that we're going to be testing on. So it's part of the stuff that is in the book. That's why you have to have the book in here and go through it and read the chapters. So today we're going to go through the objectives for this week. And I'm going to go through this stuff in here, as you have had a chance to go through it. But it may not be the entire picture. The entire picture is actually what you have to cover, because I'm going to talk about a few things, and I actually have a slinky in here to demo the waves, but doesn't mean that you guys do not read the book, because this entire chapter is part of your duty. Okay. So this is basically the stuff that I'm going to be talking about. So again, the first part is the review. So this is the objective for this week. Do the review. That is, again, discussion item number 1 today, is do the review. That is a very, very important thing in here. And as I mentioned before, it has 2 reasons. The first one, it helps you prepare for the exam. And the second one is because it's a graded assignment too. Okay, so you have to do it. Okay, please follow the instructions in the review also while you're doing that. Okay, it's going to, you'll have a limited time to do these things. The review is an open time, so you can have as much time as you can spend 50 minutes on it, you can spend 5 hours on it, whatever you want to spend on it. You can come back later on and spend more time or less time, depending on how you want to go about it. So there is no constraints on the review. There are constraints on the exam though. And again, the exam is only one chance, and it's a timed assignment. Okay. So this is a brand new topic. Again, one of the things that F equals to MA does for us is helps us basically locate an object in space and see its behavior. Okay. An object usually, when all the forces and everything else is accounted for, can be in one of 2 states. It can be stationary, like this object in here, or it can be in motion. When the forces cancel out, it's going to be uniform motion. So that's basically, in a nutshell, what we learned from mechanics. However, an object that is in equilibrium, like this ball in here, which is in equilibrium. The reason why it's in equilibrium, because it has its own weight, which is the force of gravity of the Earth on it. And it has also the reaction from my hand in this case, the support, the force of support that is pushing in the opposite direction. Both of them cancel each other, and the object is stationary. However, if I move the object slightly, it's going to basically, because there is a lot of friction, it's going to move back and forth. If you take an object like this one and put it in a ball, for example, and you move it around, you see that it's going back and forth. Okay, that behavior is called an oscillation. Actually, oops, I didn't mean for this to fall in here. An oscillation is, for example, a pendulum. I'm trying to look for a string in here. I don't have any strings in here. This probably can. This is a motor, actually. This is basically what a pendulum is. So if I wait for it to stay in equilibrium, it is actually in equilibrium more or less, because my hand is shaking. That's why you see it shaking. So there is a force of gravity in here pulling it toward the Earth, and there is the tension in the string keeping it from going down. So both of them, they cancel, and in this case, this object is stationary. But if I come in here and move it out of its equilibrium, it's going to oscillate. So oscillations are actually motions around some equilibrium somewhere. Okay. So in the example that you have in the picture, you have actually an example of an oscillation due to up and down, in this case, due to the force of the spring in this case. So there is a spring, and that spring has a characteristic, and I'm trying to look for a spring. I have a slinky in here, which can approximate it to a spring. So imagine me putting a mass in here, and that mass will go up and down in this case, because the spring has a restoring force. If you stretch the spring, it doesn't like to be stretched. It wants to go back to its unstretched condition. If you compress the spring doesn't like to also be compressed. It wants to go back to its normal length. So that is the characteristic really of the spring. Springs do not like to be stretched or compressed. They want to stay where they were. Okay. So that's the position, that's the equilibrium for them. That's really where they want to. So if you take a spring and you put a mass to it, that mass will stretch it, but then it will reach equilibrium and it's not going to go anywhere. So it's going to stay there. and it's not going to go anywhere. Unless you come and disturb it, then it's going to go up and down, okay? So those are the characteristics of the spring. So an oscillation really is a behavior in time. An object goes out of equilibrium, come back to the equilibrium, go out of equilibrium in the opposite direction, come back to equilibrium, go back out of equilibrium, and then back and forth like this one, okay? So imagine with me this line in here, this level in here is the equilibrium. So if I disturb it out of its equilibrium, it's by a certain stretch, then it doesn't like that. The restoring force in the spring will bring it back to its normal stretch, but because of the inertia, is going to keep it moving upward. So it's going to compress. Well, the restoring force in the spring will push it backward so that it goes back to its normal strength. But the inertia in the mass will keep it going so that it stretches, and then I have this oscillation back and forth. So this behavior is actually in time. It's in a sense localized in space because it's not going to go outside of this mass spring system. So in other words, this spring, let's say the green line in here is where it was undisturbed before I basically disturbed it out of its equilibrium. So what I did was either I pull it by this much stretch, or I pushed it by this much compression. It's the same thing. So you stretch the spring or compress the spring, it's the same thing. So at this position, it's fully stretched. Now the spring will pull it back. That's why it's trying to restore order, trying to restore the object back to its equilibrium. So it's going to pull it back until it comes back to the green line. But this mass has a mass, and mass has inertia. Since it's moving, it's going to keep on moving by the force of inertia. So it's going to compress the spring, actually. While it's compressing the spring, in this case, the spring resists that compression to a point after the mass stops. At that point, the restoring force of the spring will take over and then push the mass back into equilibrium. At that point, the mass still has inertia. It has a velocity. So it's going to have to continue. I mean, it has mass and velocity, so it has momentum. So it's going to keep on moving in the same direction, stretching the spring in the process. And you have an oscillation in this case, or vibration. So this behavior is localized in space. It's not going anywhere. A wave, on the other hand, is not localized. A wave propagates, move from point to point to point to point. If you go on a pond, for example, and you throw a rock, that point where the rock landed will go up and down. If you take a picture with a slow motion, if you take a movie with a slow motion, basically, and slow it down, you will see that point where the rock landed goes up and down. So that's an oscillation. But that oscillation does not stay there. It moves across the entire pond. So it spreads around. So what we have now, we have localized oscillation, but actually we have waves now that is taking that oscillation and spreading it in the medium, taking it from point to point to point to point. So a wave, in a sense, is an oscillation that propagates, moves around in space. So it's not just this temporal behavior. It's not a behavior in time where the oscillation goes up and down. It's actually that motion, but spread in space. Okay. So those are the two major differences between them. Both of them are characterized by how often you go up and down. In 1 second, how much time you go up and down? Are you going up and down, or going up and down, up and down, up and down? So this is called the frequency. The frequency is how fast basically this going up and down. So if it's going slowly, that's a low frequency. If it's going higher, that's a higher frequency. So this is a frequency. I can look at the frequency in a different thing and say, okay, how long does it take for the mass to go from completely stretched spring back to when it's completely stretched again? So the time it takes for it to go from here all the way to the equilibrium, back to the fully compressed, back to the released when it's equilibrium, back to the fully stretched, that is a period. That is a time. The time it takes for a whole oscillation. That's what a period is. The period and the frequency are the inverse of one another, basically. If I call the frequency, the number of times you go up and down is 1 second. So you could go 1 back. This is 1 second. That is 1 oscillation per second. Or I can go 2 oscillations per second. Or I can go 3 or 4 oscillations per second. Or I can go crazy like this one in here and do probably 10 oscillations in every second. So that is the frequency. And the period is the time it takes me to go once. In the first case, it's 1 second. In the second case, is actually half a second. Because if I do 2 oscillations in 1 second, each one will take half a second and the other one half a second for a total of 1 second. So 2 oscillations in 1 second amounts to half a second each. If I do 4 oscillations up and down, 4 times in 1 second, that means each one of them will take quarter of a second. As a matter of fact, the relationship between the frequency and the period is just this simple relationship. The frequency is just the inverse of the period, that's all. Well, the period is measured in second, which is a time really. The frequency is measured in 1/2, or in honor of Mr. Hertz, we call it Hertz, okay, Hz. So that's the unit for that. Both the oscillation or the vibration and the waves have this 2 characteristics. They both have a period or a frequency, and the period and frequency are related to one another, okay? Now, sometimes we refer to them in angular measurements, in angles. Because if you take an oscillation and you project it on the screen, it's actually a rotation. Let me explain this relationship in here, which is critical. So let me go back in here. Let me find this screen and let me add to it a new page and let me call it speed 10. Because sometimes we miss this point in here. So let me explain it here at this point in here. It's really not a big deal, honestly. But sometimes there is a subtlety in it that we really have to look at it. What is my pen? Okay. Let's say, for example, this is my desk right now, okay? I'm looking at it standing up like this, okay? I'm looking at it from the top. So this is how it looks to me, okay? And if I take string, for example, make a hole in the desk, and under the hole, there is a piece of string in here, and the string, for example, attached to it a mass in here. And I spin this mass. This is going in a full circle. The radius of the circle is the length of this string, okay? It's going on a full circle. And I can ask, how much time does it for it to go a full circle? That is going to be a period. It doesn't matter where I take it, okay? I can take it from here, and if it's in uniform motion, it's going to take a whole period t for it to come back. So that's a period, okay? Or I can ask how much time for it to go in 1 second. How many times does it go in 1 second? It could go one whole period in 1 second. That means the period is 1 second. So if it's 1 second, it goes once around the circle, okay? So I can describe that by the frequency. If it's going too fast, in 1 second, it goes twice. The period, the frequency in this case is 2. That means in 1 cycle, it's a half a second because it will take 2 cycles in 1 second. And so on and so forth. So it's still true that the period and the frequency are related to one another through this relationship, okay? Or if you wish, F is equal to 1/t. It doesn't matter which one you write, okay? So that's one way of looking at it, okay? But this is an angle. This is actually 2 pi angle. That's an angle. That's a 2 pi angle. So I could say how many times it goes once around the how many times it goes in 1 second, or I could ask how many times it goes for 1 full 2 pi or circle. It's the same question, really. 1 cycle is 2 pi degrees, 2 pi radians, that is, which is 360 degrees. That's exactly what it is. So instead of measuring it in F, we use the symbol omega, which is 2 pi F. So omega and f are related with one another, and the difference is just 2 pi. So sometimes you hear me use the word frequency. I don't necessarily mean regular frequency. Sometimes we also mean the angular frequency. So the symbol in here, omega, is what we call the angular frequency. It's the same measure actually, except it's measured in angles. Okay, you're not convinced that this is actually an oscillation. Let me do this trick with you. Okay, let's look at the disk, not from the top, as I was standing earlier, but look at it from the side, okay? Look at it from that side. So this is how the disk look like to me from the side, okay? And there is a mass in here. So there is a string attached to it in here. The mass is moving around. It's going in a circle. But as far as I'm concerned, it looks like it's going back to the center. When it's completely on the opposite side from me, from when I'm looking, the mass looks like it's in here. So this position corresponds to the mass being, let's say, for example, this is where I'm looking at it. So the position is here. So it looks like it's just on the center. So it has moved all the way the quarter side from the circle. It looks like it's in here. Now, if I look at it still, it's going to go around now, and as if it increases, and it's still, and now it looks like it's in the opposite direction. So it looks like this is the direction I'm talking about in here. Okay. Oops. It's in this direction. So it looks like it's in the opposite direction. So it was here, it moved way back, now it fully moved the half circle. So as far as I'm concerned, it moved the whole from here, because I can't see the top. I'm looking at it at the side from the disk. So I see it moving back until it's completely in the center, back on the other side in here. Now, while it's moving, it's going to come back in here, and then it's going to be at some point in this position, which is aligned with the center, actually. So at this case in here, it looks like it has actually went down in here from my projection, and now it went back. And if I keep on watching it from this side, it looks like it went this way. Now it's fully stretched as it. So this is a full cycle. It goes from fully stretched string to completely compressed spring until fully stretched one. So this is a full cycle, corresponds to full 360 degrees on the rotation. So the rotation and the oscillation are related to one another, hence the number 2 pi. The 2 pi is 360 degrees, okay? So sometimes instead of measuring it in actual frequency, we measure it with the angular frequency, with this measurement of the angle. And physicists, actually, this is common only for physicists, okay? They usually use the same word for both of them. For the frequency and the angular frequency, they use the word frequency. They don't want to carry that word angular. Although sometimes they clearly are referring to the angular frequency and the frequency, because the difference between them is just 2 pi. 6.2. 2 pi is a number, by the way, it's 6.28. So just between the difference between them is 6.28. which has no units. It's really and sometimes physicists, like when they're talking about angular frequency, to make the distinction is this unit they use for it. So if you hear a physicist or a textbook and they tell you the frequency and they tell you 320 hertz, when they say hertz, they mean this one. When they tell you it's 320, for example, radians per second, they mean this one. So the units are giveaway. But that is a subtle difference between the two, and it's really inherent in the spectra in here. It's the same thing. It's absolutely the same motion. Whether you look at it from the top of the desk or from the side of the desk, it's the same motion. So circular motion, from one angle, it looks like it's an oscillation. Hence this relationship between the two, okay? So that is really the part that you're, that is related to that expression in there. Let me go back into my notes in here, share. So this expression in here, so that you guys know where it's coming from. Obviously, the frequency is still 1/t, so sometimes it's written as 2 pi over t. So that's where the roots of that expression are coming from, that's all, okay? So when you see 2 pi in here, you understand that there is a rotation somehow, there is a cycle. And the word cycle actually is used also in here too. So if I look at a wave, first of all, there is another concept in here, the amplitude. Because I didn't tell you when I stretched the spring, how far did I stretch it? Did I stretch it just a little, or did I stretch it too much? Okay. That is the amplitude. How much really is the disturbance, which is critical. Because if I stretch the spring too much, it could stretch beyond repair. So the spring has a tolerance, actually. And that tolerance is called the elastic region for the spring. After that, it becomes non-elastic. It won't restore back to the equilibrium. It's going to stay deformed. You don't want that, okay? So every material, regardless of what it is, has this tolerance for elasticity. The building where you are right now, your home, or if you're on campus, it doesn't matter, can swing back and forth due to all kinds of things. Yes, you might tell me, okay, this is the house, it's strongly built, but give it enough disturbance, it could sway one way or the other. I'm thinking about earthquakes. Earthquakes are actually waves too. So they could actually take a whole building and start to move it back and forth. And if the earthquake does not have a high enough intensity, all you see is just that motion back and forth. And there is a restoring force similar to the spring that restores it back to its equilibrium. But if the disturbance, if the earthquake is strong enough, the building could go out of basically, it will not be able to restore back to its original state, and it might collapse or basically is destroyed. So again, there is an elastic field for everything. I mean, if you're outside probably watching this one on your phone and you're near a tree, the trees also oscillate, the wind actually takes its leaves and oscillates. So the oscillation is actually a common phenomenon. And the disturbance, the waves, actually is a common phenomenon. It's actually so common that almost everything that you see behind, next to you, is actually propagating in one wave or the other, okay? So this is the other characteristic, and that is the amplitude. So the amplitude can be a big deal, okay? It is usually a big deal because it carries how much energy can be transported, okay? Yes, the frequency is important in terms of the energy, which is another point in here. Because if the wave is a propagated disturbance that moves in space, also in addition to the fact that it changes in time, so what does it carry with it? Because if I look at the surface of the water, for example, and if I happen to be on a boat, for example, on the ocean, and there is a wave that comes in, it's going to carry me up and down. So I go all the way to a crest when I'm at the top, and then all the way down to a trough when I'm down. But then I'm going only up and down. I'm not coming to the shoreline, or I'm not receding from the shoreline. So what did the wave do then? If it came all the way from the middle of the ocean or from the tsunami somewhere, and then comes all the way to the shoreline. Then in this case, the wave, what it did bring with it is energy, because it actually can do damage on the other side of the string, or the other side of the stream, or the other side of the ocean, or the other side of whatever you're looking at, whatever wave you have. So the wave carries it with it energy. I didn't talk about sound, and we have a whole section about it, so we're going to talk about that. But sound itself is actually a wave. And that wave actually starts from the vibrations, again, in the mouth, if you wish, or in the disturbance that you create, in this case, compression of the gas. And actually you can hear it too. And that gas starts to propagate from point to point to point to point until it reaches a receiver, and that receiver actually will carry that energy with it and give it an interpretation. For our ears, that's exactly how they function. So our ear canal will receive the sound waves, and that takes the drum of the ear and moves it in and out. So if there is a compression, it's going to move the drum inward into the ear. Or if there is a rarefication, lack of air, it's going to yank the drum out of its location. So basically it moves it in and out. That motion, depending on how far it can go in and out, is the intensity of the wave. If it's too much, it can rupture the drum. That's one thing. And a person can lose hearing that way. And also, depending on how far it goes in and out, or if it's going in and out, or if it's going in and out, that is the frequency, that is the tone that our brains interpret and gives us different kinds of tones. Either a low pitch or a high pitch, basically, depending on how you can see it. A small kid, for example, or a small baby produces usually a higher frequency or a higher pitch. An adult, especially a male, will produce typically a low frequency. Okay, a big animal like, for example, whales and elephants, they produce usually longer frequencies, much longer frequencies, which means that their ear drum probably is much larger than ours to basically be able to capture those low frequencies and actually change with them. Smaller animals like bats, for example, they produce extremely high frequency to be able to communicate with them, okay, that we cannot hear. So that is basically, and we cannot hear also the low frequency either. So we have only a range of hearing that is available to ourselves, just as much as we can see only with a range of frequencies. So again, this is the characteristic of a wave. So one of the things that I mentioned already is the wavelength. The wavelength is the distance between crust to crust, or trough to trough, or any point similar to any point similar. So you tell me, okay, this level of the wave is the same level of this wave and the same level of this wave. So why did you say the wavelengths are from here to here? Well, in this case, the wave, in this case, if I'm looking at the ocean, it's rising, okay? Whereas this one is going down. This one is rising, so it has to be similar points. It can be, for example, from position of equilibrium to a similar position of equilibrium, because you might tell me, hey, this position of equilibrium is similar to this position of equilibrium. I mean, it's the same position of equilibrium, so why did you skip this one and move all the way to this one to tell me that this is the wavelength? You have to look at it also in the same fashion. Is the level going up? In other words, is this mass going up? If it is going up in this case, then it has to be compared to the going up, because this is actually coming down. Remember, the mass was stretched, the spring was stretched, and now it's compressed. So we are at this position. It's compressing back into the equilibrium. So now we're fully compressed, we're here. And now we're stretching back to equilibrium position, but we are stretching, we're not compressing. Remember, this position was where we were compressing. This now we're stretching. The mass is moving in the opposite direction until it's fully stretched, where we are here. And then we are now going back into the position of equilibrium from the stretch position. So we're decompressing. So this is decompression, this is decompression, and they are similar position. Both of them are in equilibrium, whereas this one is a compression. This one is a, sorry, did I say decompression? This is a compression, and this is a compression, and this is actually the decompression. We were compressed, fully compressed, and we're going back into the stretch position. So this is compressing in position of equilibrium. This is compressing in the position of equilibrium. Whereas this one, it's decompressing in the position of equilibrium, so it's not similar. So it has to be similar to similar. Easier way to do this is look at the high intensity, the peak, and look at the high intensity, the other peak, and the distance between them. Now, the wavelength is actually distance. It's in meters. Distances are always in meters. Between crest and crest is a distance. So if you're a fisherman sitting in the ocean and trying to catch your fish, and you see waves, you can estimate the distance between crest to crest, and you find the wavelength. Is it 1 meter? Is it 5 meters? Is it 7 meters? Is it 3 meters? That is the wavelength. And if you know how up and down you're going, okay, let's say, for example, you're going up and down 5 times in 1 second. The ocean is going up and down, up and down, up and down, and you're looking at the wave coming from you, and it's, let's say crest to crest is 3 meters, for example, and you're going 5 up and down. So in this case, you can find your wave speed, how much the waves are moving when you're. Remember, the distance between crest to crest, I say it's 3, and you're going up and down 5. So your distance, the wave now is traveling with a speed of 15 meters per second. It's a super fast wave because it's coming to you. You're up and down 5 times in 1 second, and they are separated with 3 meters apart. So you could use this law to find how fast the wave is moving. So if you're a fisherman, when you're sitting on your boat, you can say, okay, We went up. I'm looking at the watch. Went up and down, up and down, up and down. How many times I did? 5 times? Okay, 5 times in 1 second. Good. So I know the frequency now. Okay. I see one crest and I see another crest, and the distance between them looks like it's 5 meters. So this wave, ocean wave in here, is moving super fast. It's moving 15 meters per second. It is a big number, by the way. Okay. So it's converted to miles per hour. Okay. You see, it's a big number. So it's not that big. It's not like 50 miles per hour or something, but it's big. It's a fast wave in this case. So it's carrying a lot of energy with it. So again, so a wave has a wavelength that the oscillation does not have. A wave have a wave speed, which is simply the product of the wavelength and the frequency, because waves have this too. Waves have the stuff in here. So both of them have this. Now, vibrations do not have this. You're asking about this one in here, and you're absolutely right. This mass has a velocity going up and down because it's going up and down, so it has a velocity. But that's a localized behavior. It's not stretching in time. So a wave, on the other hand, on the ocean is moving from point to point to point to point. The person who's going up and down on the boat, fisherman going up and down, yes, he's got that velocity of going up and down. But what I'm talking about in here, the wave velocity, is that disturbance going from him to the other side of the ocean. Okay, that is another story. Let's say, for example, the intensity of the wave in that case is 1 meter. So he's going up and down, up and down. So remember, for him, he could have a 0 velocity when he's fully in the trough, because he's coming down. When it comes to the trough, he's going to stop and turn around. And then at that point, moving super fast, then go to the crest. At that point, he's going to stop completely and then turn around. So for this velocity can vary from 0 velocity to a maximum velocity in this case in here, which we can find, okay? Which we can measure. But we don't care about that. What we care about is the velocity for the wave going from point to point to point to point. That is really the characteristic difference in here, okay? So there is a velocity in here, but that's not the way, because we're talking about propagation in space now, okay? Hopefully I did not confuse you in that. Again, this is the birdie doing the same thing. If I take the waves, there are 2 kinds of essentially waves, okay? There is the so-called compressional waves or longitudinal waves. So if I take this link in here, and if I compress it somehow and let go of it, you will see that the compression moves along the slinky. So this is an example of a longitudinal wave, sometimes called the compressional waves because it's a compression. If I take the slinky now and move it back and forth, this is an example of transverse wave. So waves are essentially 2 kinds. Compressional waves, you see here, there is a compression, there is a compression, and there is a compression in here too. And there is a compression near the hand in here. But you have to continuously do this, pump it up and down in order to see really the wave propagate that way. So there is a disturbance in here, and that disturbance is actually an oscillation. So the hand is going back and forth, back and forth, back and forth, back and forth in this case. So that is actually an oscillation. But each time it's producing those oscillations that move along the slinky. So in this case, you have a compressional wave or longitudinal wave moving in this way. I could do the same thing with the hand, but instead of moving in and out, I could do up and down in this case. And the disturbance now is not along the slinky, but it's perpendicular to the slinky. The slinky is stretched in this direction, but the slinky is going up and down, up and down, up and down. And here, it's at its up or crest. In here, it's its up or crest. And in here, it's its up or crest. In this position, it's a trough. In this position, it's a trough. This is actually the equilibrium because it's fixed to the wall. And the hand is moving so fast in this case that practically you can consider this one also the position. This position to be equilibrium. Okay. Sound waves, I already mentioned, they're of this type. They're compressional waves because it's the air that is being compressed While it's compressed, it's going to pull the air from its side and becomes rarefied. So it's really this compression followed by rarefication, followed by another compression, followed by another rarefication that moves around in space. And it moves in a sphere around you. And because of the wavelength, the characteristics of sound, they have typically a long wavelength, they can go around buildings. As a matter of fact, they go on the building. So if you don't have a soundproof wall, people next door can hear you, okay? So although it's attenuated versus the people who are in the room where you are who can hear you louder, but the people on the other side can still hear if the sound is high enough, but they will hear it weaker. But it's still, sound can propagate. It can be captured either by an ear or an electronic device. And in either case, it's going to be converted into an electrical signal, because once the ear captures it, it goes through a very complex system. And then at the end, it's converted into an electrical signal that goes to the brain. And the brain will capture that and gives you a sensation of how it sounds, okay? Give you a sensation, an interpretation of the intensity and the frequency. So those are the two key things when it comes to sound. Because if the intensity is too low, extremely low, your ear may not capture it. But if the intensity is too big, then it might be too loud to a point that it becomes hurtful. So people decided to come up with a scale. They called anything that has very low pressure, because again, it's a pressure on the ear, that's all. That is, below that point, it's basically you cannot hear. And there is a value for that pressure, 10 to the negative 12 Pascal, okay? So they call this one the threshold of hearing. Instead of using this number, they use a logarithmic scale again. And the logarithmic scale is useful in this case because it can give me a moving from one power to the next power, only one motion, 1 degree, okay? They call it the decibel, okay? That's the unit used for the threshold. So 1 decibel is the threshold of hearing, really. If somebody talks less than that, you cannot hear them. If something produces sound less than that, in terms of intensity, you cannot hear it. It's below the threshold of hearing for normal people, okay? Then there is a level where the whisper becomes noticeable, all the way to 120, where painful, basically, sound starts to be produced. Sound that is 120 decibels, which is the equivalent of 1 bar. Oh, no, 1 bar? Did I say that? It's yeah, I think I gave you the wrong. Yeah, it's 1 Pascal, okay? So in this case, you are talking about tremendous amount if you're talking about power in terms of pressure, but a huge pressure nonetheless that can start to cause pain in the ear, actually. That is actually the threshold of pain. After that, around 140, 150 decibels, which is typical sound for airplane taking off and other kinds of huge sounds that you can hear, that seriously can be damaging to the ear, okay? That is actually where ear can be ruptured, because it's going to be yanked in and out, bang, with that much intensity. You don't want that. That's too much, okay? So again, sound is really an example of a wave. Can you hear a sound if you are outside in interstellar space? Absolutely not. I know when you watch movies, especially sci-fi movies, there is that music in the background and somebody drops, for example, whatever they're carrying with them, and you hear it bang, you hear it there, and you hear all kinds of noises in the background. Unless there is air, you cannot hear nothing. Outer space there is completely quiet, as quiet as it can get. Because there is no particles in there to carry sound for you. So you could be standing next to me. And for example, you have your ears reading your phone or something, and I could be in front of you and screaming my head off. You cannot hear me. Why? Because there is no medium in them. And of course, if there is an electronic device that takes our sound, converts it in an electrical signal, sends it back to you, you can still hear me in your enclosure. But that's another way of communicating in there, okay? So again, sound requires a medium, and it travels this way. All waves have these properties of reflection and refraction. On a glass mirror, for example, when you stand up, what you see on the other side is your own reflection. sound also reflects off of media. When you're talking, sound actually bounces off. Some of the walls, they do not really reflect well because of the fact that they are absorbent. They absorb sound for the most part, okay? Their molecules starts to move around, and then they disperse that energy instead of reflecting it back. Okay, some places, like for example, in a container like this one, you would want actually the sound to reflect better. So if you are in a musical hall or something, you would want to produce enough reflectors in the room to reflect sound back. Okay, so that you appear to you that sound is coming from everywhere, and it's really a nice feeling. So the engineers that work very hard to make a elliptical really environment where sound reflects evenly from all directions. So you need really an ellipse, and you put the singer or the group right in one of the focal points so that sounds appears to be coming from everywhere in the same time. Otherwise, there will be a delay. Somebody says something, it comes from one side this way, and it comes from the other side that way, and starts to come up with the interference patterns, which is another behavior of waves that we're going to talk about, that can damage the whole quality of sound and becomes really a kind of a mess. So yeah, that's why usually either a full elliptical or part of an ellipse, because ellipses have a very good characteristic that they are the same distance, no matter which way you go to them from certain points, similar like the circle, which is the same distance from a single point. Anyway, so in this case, the reflections, they all come back in the same, no matter where you are sitting, basically in the hall. That's the part of the engineering. The other thing, and that's a key thing in here, and that is to have them reflective material so that sound appears nice coming from everywhere. Now, in addition to that, sound has actually a refractive behavior. Refraction is similar to when you stand in front, and we're going to talk about this when we do optics, by the way. When you stand in front of the pond and you take a, doesn't matter, pencil or a pen or something, or not a pond, let's say, for example, a cup of water, okay, in a glass. So you put it in, and the pen looks like it's broken. Looks like it's kind of making an angle. That is what the refraction is. As the wave hits the separation between two different media, in this case, in the example I mentioned, the water and the air, the wave in this case changes speed. It's not moving with the same speed from medium to medium. So it appears to be refracted. It has to travel at a different direction to basically do the least path possible in this case. Okay, so that's the principle that we're going to be talking about when we talk about optics. And this is true for all waves, actually. As I was saying in here in the example, in this case, on a day, if you go outside, for example, and you scream or you talk to your friend who's on the other side, for example, of the field, soccer field, or you call them, they might not hear you well. The reason why, again, is because the way, in this case, the sound is propagating. Again, in this case, the sound is propagating during daytime. You have the warm air in the bottom and the cool air in the top. And the way that the wave is propagated is going to be a spherical object in this case, but it's going to bend upward. And the wave will follow the path of that is normally for each single wavelet, in this case, for each single basically wavefront, is going to, at least the speed in this case, is going to be perpendicular to this wavefronts as they are moving from point to point to point. And because of this characteristic of how the wave is actually forming, the sound will propagate for the most part on the other side, and the other guy will hear a sound probably, but not as loud. They don't hear it as clear. They don't understand what you're talking about. Hey, can you move there? They don't understand. Can you, this is, no, I'm trying to play golf in here. Can you move to the left or to the right or something? Yeah. Can you repeat what you just said? I did not hear you. And you can have very bad conversations. Okay? Unless you pick up the cell phone and call the other person, you're not going to be hearing very well in this case. But in the evening, it seems like when you're talking, hey, look at the way that person is dressed. And they can hear you. Okay, from the other side. Why? Because again, you have the cool air in this way, and you have the warm air in the upper atmosphere. So now the bending is actually backward. You really don't need to shout that much. I mean, probably you can experience this one the day and night. You go camping and you go to, we do that from time to time. We go to the Joshua Tree for basically stargazing, and you can hear faint sounds from far away. Whereas during daytime, you can't hear nothing. Okay? You can hear just your immediate vicinity. So it's really a fascinating thing in here. It has to do with how sound bends around objects, just like as much as light, what we're going to be talking about. One of the characteristics of waves, actually, they have this thing in here, which can explain, first of all, resonance. Resonance and beat is another phenomenon. When you have a wave coming from one source and another wave coming from a different source, they may be in sync. No. Let me repeat that. Okay, let me repeat that. Objects have natural frequency. For example, in the example that I mentioned, for example, for the building itself, it has its own natural frequencies. I mean, if you move it, it's going to oscillate in that frequency. Now, when you are forcing it to oscillate, you could or could not be in resonance. Let me explain what that is. Let's say, for example, a child is sitting in the, child is a bad example. I don't want to use the example of child. I don't want to use the example of a dog either. But let's say, for example, there is an object oscillating in the swing, okay? A normal swing in the park that you find. Typically, the example is about child in here. And let's say, for example, each time that child comes back to you, you're sitting in this position, you push them back. So now you push them or pushed her, she's on the other side, and now comes back, and then you push them again. And then you push them again. Each time they come back, and let's say ignore friction, each time, because if you push them only once, if there is no friction, they should go back and forth, they will never stop. That is really the reason why they stop at all. The reason why the slinky stopped in the beginning is because of friction. So let's ignore friction for a moment, okay? Because friction is a damping effect in this case. So if you swing them once, if you push them once, they will go back and forth, and they will never stop. But if each time they come back, you push them again, then in this case, you're adding more energy to their oscillation. Next time around, when they go further out, because there is no friction to actually slow them, so you gave them more energy. So if you keep on doing this, forcing them to oscillate more and more, they will gain more and more amplitude, gain more and more energy. And that could be damaging to a building. The child actually could fall off in this case, and that's why it's a bad example to use the child. So the building could be oscillating, and if the frequency of the forced frequency and the natural frequency of the building are in sync, this could lead to damage. That is the resonance. So in this case, this lady in here produces a similar frequency to the natural frequency on the other side. That sound would be captured, and this one starts to oscillate. And it's going to oscillate violently too. It's going to oscillate with a high amplitude. So if she keeps on producing sound and sound and sound, the other one will also respond more and more because they're in sync, they're in resonance. But if they're not in resonance, then it doesn't matter. This will not produce, if it produces hardly any kind of oscillations, but they're not going to be problematic in this case. Okay? The response in this case. So there is two things in here you have to remember. You have the forcing agent and you have the response. If these two happen to have the same frequency, then we have resonance. If not, then we don't. It's like the tuning device on your radio. In the old days, we have dials in the old radios, or even in the TV, we have dials. We had dials. So what we're doing when we dial a tone, when we dial a frequency, we're changing the internal frequency of the radio to match that of the station we would want to listen to. We were listening into this station and we don't like it anymore. So we go to the tune in, we change the frequency, and all of a sudden our radio now is in sync with another station. So we're capturing the second station in here because they're in resonance in here. So we take it out of resonance from the first one and put it in resonance with another one, and so on and so forth. So that is why resonance is a very, very important phenomenon that we study. In addition to that, there is actually also another phenomenon, especially with sound, I mean, with all waves, is that when the waves happen to have the not exactly the same frequency, but close to enough frequency, then there is a hum that is going to be produced, and those are beats. That is the beat frequency that is produced in this case. Okay, so again, those are some of the stuff that is related to. And why waves do all of this? This is a good case of the Tacoma Bridge. And when they built it, they didn't realize that the wind can blow in a similar frequency to the bridge. So as the wind started to blow, then it was really in sync with the bridge, and the bridge kept on oscillating more and more and more until it fell down. So now if you're an architectural engineer, or if you are in this case, civil engineer, you have to be careful with these things. You have to really make sure that the natural frequency does not match any of the forced oscillations that may be produced in the region where you are, if you don't want any damaging effects in here. So resonance can be a good thing, or it can be a bad thing. In this case, it's a bad thing. Resonance actually is a useful device for the tuning of devices. So you have to be careful with that. Waves interact with one another. That is actually characteristic only to waves. So when you see interference patterns, like for example, if you go on the ocean, on the pond, and you throw two rocks in two different points, one of them will create its own waves, and the other one will create its own waves. And where the waves meet, they will create a pattern unique to waves. There will be places where the waves cancel each other completely. That is called destructive interference. There will be places where the crest of this one and the crest of that one will make it even a bigger crest, or the trough of this one and the trough of this one will make even a bigger trough. That is actually constructive interference. So there are places where the amplitude is much higher than the initial amplitude, or the amplitude is much lower than each and every one of them, or there is no amplitude whatsoever, depending if they started with the same amplitude. If they did not start with this, in this example, we started with the same amplitude, so there will be a reinforcement in this case. This is a constructive interference. Since we started with the same amplitude, and when they are out of phase in this case, and they are out of phase by 180 degrees, they will cancel each other. Remember that 2 pi that I mentioned before? It comes into play in this case to explain at least what's going on in here, because the 180 degrees is exactly what is needed to have these cancellations. So this is a reinforcement, which is usually 360 degrees or 0 degrees or any multiples of 360 degrees. This one is actually 180 degrees or 300 and or 200. 300, what is it? 360 plus 180, and do the math, okay? So that is basically the whole thing. Half wavelength, if you wish. Half wavelength, or multiples of half wavelength, 3 halves wavelengths, or 5 halves of wavelengths, or 7 halves of wavelengths, or 9 halves of wavelengths, and so on and so forth. This is a full wavelength or 0 wavelength difference between the two, or 2 wavelengths, or 3 wavelengths, and so on and so forth. That is one constructive interference. Provided we start with a similar frequency, if we, similar intensity. If we don't start with a similar intensity, this effect will not be completely seen in that. There will be almost cancellation, but not cancellation. And that is the device used for noise, basically cancellation errors, things that is used in the airports by the people who work in the airports for noise cancellations. They use similar frequencies that is produced in the field, but out of phase to cancel the effects of the waves there. So the device isn't smart enough to pick up the frequencies that are picked up, that are being sent to it, and then produces similar frequencies, but out of phase. So to cancel the noise. So it's really a good device to have it. So if you're working in the airport, you don't want to lose your hearing just because of the fact that you're working in there. The last point in here, or at least the point before last, or 2 more points, okay. I'm sorry, is, and it's related to resonance actually, is the standing waves. If we have one end and the other end are fixed, then we can clearly create, like the string, for example, on a musical instrument, can create standing waves. And standing waves, they are characterized by this peaks, if you want to call them peaks. These are called antinodes. So I have one antinode in here, and I have 2 nodes in here. In this case, I have 2 antinodes, and I have 3 nodes in here. And in this case, I have 3 NT nodes and 4 nodes. In general, if I have a certain number of NT nodes, I have one more for the nodes. So this point is stationary, it's not moving at all, it's not moving at all, it's not moving at all. Those are called nodes. NT nodes is when the amplitude is its max. There are points in between that. So this is usually produced by musical instruments. And even this one also can produce standing waves. And in this case, it's an example of another one. If you take, for example, a string and you snap it from one end, it's from one end, it's fixed, from the other end, it's not. This is similar to it. So you can have both ends fixed, like this one's in here, where it's clearly where the nodes and NT nodes are formed, or you can have one end fixed and the other end can snap back up and forth. So this end will always be an NT node if it's not fixed. But if it's fixed, it's always going to be a node. And this end is going to be a node in this case. So you could have that scenario also, but it's still clearly formed by NT nodes and nodes. This is a one-dimensional example. On a two-dimensional surface, for example, you can have also nodes and NT nodes forming. But for example, if you take sand and put them on a big drum and you start producing sound, you can clearly see the formation also of this thing on the two-dimensional surface. You can actually have it in three-dimensional surface too. So again, it's three-dimensional objects too. Okay, so this is a pattern, and it usually has to do with the reflection wave and the incoming wave interacting with one another. So here is the deal. Somebody produces a wave and it's going to travel along the string, and then it's going to reflect from the other side, depending on if the other side is free or fixed. This one is fixed. So it's going to reflect back in the opposite direction, and this there will be standing wave as long as the frequency is the right frequency. Okay. So this is an example of this kind of constructive and destructive interference. The incoming and the reflected. Same thing in here. But now the frequency is just high enough for it to produce 2 NT nodes and 3 nodes. This one is frequency is high enough for it to produce even 3 NT nodes and 4 nodes, and so on and so forth. So this is an important phenomenon, resonance. This is actually resonance too. This is the standing waves called, okay? Before I get into the bow waves and sonic boom, there is another effect called the Doppler effect. And the Doppler effect you have experienced it. If you're standing in near the freeway, for example, or near a car, for example, moving in, even if you are not looking, you can tell if the car is incoming or not. As the source, so we have 3 things in here. We have a source of waves, which is in this case the car. The sound is actually another effect. And the third one is actually the observer, the person who is sitting, listening to it. If the observer and the source are closing in on one another, the frequency will go higher. If they're receding from one another, the frequency will go down. So the Doppler effect is an important effect in here. Okay. So the Doppler effect is an important effect. It is actually used by the police officers to detect how fast you're moving. They use a radar gun. Based on that number that they get, they can tell exactly how fast you're moving, and they can use it to argue. Depending on if you're moving away from them or going to them, they can use it actually to detect your velocity. It's actually a critical piece in here also when you understand waves. So here is the deal. As the source is broadcasting its sound or its wave in general, it's going to, if it's moving toward the observer, it's going to produce it and move toward them. So in this case, the crests are separated less and less, and they appear to have higher and higher frequency. If it's receding away from you, so it produces a wave, and the crests are separated by a certain wavelength. That is the definition of the wavelength. But if it moves away, they appear to be stretched in wavelength and the lower frequency in this case. Remember this relationship that I mentioned in the beginning? The velocity of sound is the velocity of sound, which is 340 meters per second. So that's a fixed number. So if the distance between the crests appears to be shrinking, the frequency must be going higher. So as the source is moving toward you, and it appears to have shrunk the distance between the 2 crests because it produces a wavefront, and that wavefront reaches you, and then moves towards you and produces a second wavefront. So the distance between the two wavefronts appears to be shorter. So lambda is shorter, the wavelength is shorter, the frequency for you appears higher pitch, and that's exactly what you hear. But if it's receding away from you, it sends a wavefront to you. That wavefront will reach you and then moves away and sends another wavefront. So the second wavefront, instead of separated by this distance, appears to be moving separated by a higher distance, depending on how fast the car is moving away from you. So now in this case, it appears to be lambda appears to be longer. Since lambda appears to be longer, the frequency has to be less. And this is a big deal because this is how basically we know that the universe is expanding, because when Mr. Hubble, no, what am I talking about in here? I lost the names in here at this point in here. Yeah, I think it's him. Okay, I've been talking for more than an hour. I forgot names now and dates. Anyway, the point being in here is he discovered that for light, the frequency is actually shifting toward a longer wavelength, toward the red. That's where the red shift is coming from. And that's how we discovered that the universe is expanding. And it's used, like I said, in practical applications, at least on Earth and here for, among other things, is for a police officer to detect how fast you're moving. The last point in here is the sonic boom. And again, now we still have almost the same Doppler effect we're talking about. So you have a plane in this case, and it's moving and producing sound. If it's moving below the speed of sound, then in this case, sound has time for it to move forward before the next wavefront is sent. So it's always going to be indicative that the incoming plane is coming. If you're sitting in here and there is a plane coming from that side, the wavefront will reach you, although the separation between them is less and less, but you can tell that it's coming. But if the plane is moving with supersonic speed in this case, so it's going to produce a wavefront and move past the wavefront and produces the second wavefront. So the wavefronts now are lagging behind the plane. So in this case, the plane will reach you or go above your head before you hear the sound of the plane, okay? And there is a pileup of wavefronts on this cone in here, which is the sonic cone that forms. And that pileup will have a higher and higher intensity. And when it reaches you, you're going to hear a boom sound that you're going to do. How big is this cone? Depends on these angles. And this angle depends on how fast the speed of sound versus the plane is. So this is really in a nutshell what this whole thing is. So we completed the whole thing. I'm glad we did. I know we're probably at the end of the time. So let me go back into the home in here. This does not replace, again, reading the unit. So please read it and understand what's going on in here. So we have the lecture notes in here and we have the exam review. So the discussion point in here today is do the review. Okay. And it's going to expire this Sunday. Sounds good?
Yes.
Okay, very good. So we're done with this unit. This is not part of the exam, by the way, this unit or this chapter. And next week, since we have the exam, we're going to have basically a half chapter from chapter 11. And then we're going to finish the second part on the week after. Okay. So that's basically in a nutshell what we're going to have next week. So let me stop the recording.